Okay, let's get started. So I was talking about why this variable is so complicated and how do you figure it out. And I said I'm going to show it to you once I run the program. And those variables start right here. So just to remind you, I figured out that the circumference is C, and then I calculated the time it takes with the assumed velocity to go around the circumference. And then I pack the velocities into the variable, VEL, MSG, dot, linear, angular, etc. And I'm getting ready to start driving the robot. I initialize the part variables. And then this one, we were talking about ROS rate. So this ROS rate object allows you to monitor time using a ROS function. So ROS rate 10 is a rate object that is set up to run a loop at 10 Hertz. If you use it appropriately, the example is right here in this reference link. So I begin by resetting R, because that's like a stopwatch that I reset so it's ready to count again, right? Because it's forever counting, but now I'm ready to time the loop, so I reset it. And then here is the main loop. So this is the most important part. All the rest is set up. So in RTT, which is my test variable of the while loop, I pull in the latest elapsed time. Now, how do I know this? It's because you have to go and get the help file for the rate object right here. The MATLAB link here, this one. So all the details are there. I get the latest elapsed time, and then I start driving the robot. So this is when the robot is going to move. I get the latest odometry, so it's a copy of whatever I did outside the loop. This one just produced the first point. Maybe it was not needed because robot, well actually it is needed because I started moving the robot, so this point will be after it has started moving. So that's a good idea to get the first point up here and then get it every time within the loop, right, that it's encountered. Again, I increase the size, I augment the MATLAB variable. As I said, it's not a good idea, but I'm going to do it anyway. And then I burn the rest of the loop time. When it comes out, I have to stop the robot. This is a situation where the loop will not be eternal, because I'm asking you to go around the circle. If my logic is right, it should come out of the loop. I zero out the velocities, and then I publish the zero velocities, and then I plot the path. Shut down the robot. Is everyone clear about the structure of this program? So now we're going to run it. So let's get ready. So unfortunately the MATLAB screen is sitting on top of the gazebo screen, so I'll have to flip it, hopefully just once and not back and forth. MATLAB, and then I can go to the screen. So I'm going to run it. Oh, I don't want that. I want to get rid of that. Remove. What happens? The whole thing is okay. Anyway. Oh, okay. Next. So it's coming all the way around, and hopefully it will stop right there. You see the stopping motion? Because when you break it, right? Now this is a simulated robot. Why is it spinning this way and not the other way, right? So something in the way they have programmed it, when you stop it, it causes it to go this way. I've never seen it go the other way. It's like a car with some misalignment problems, or the brakes are not even. So the answer lies in whoever programmed it. Okay. Oh, the plot is here. Now that's not it's just a glitch. Okay. If I do it again, you see that it fills out that. Over here, see, it stopped a little bit short. Can you see that? It's because we are measuring time. We're not measuring distance. And this is what happens when you have an open loop control system. You will not be able to close or get the target you want, because then you should be monitoring the variable you want, right? We are monitoring time in order to get to distance. That makes it an open loop system. Let me run it again. Now, before running it again, because I don't have that cancellation part of the program, I should really reset it. I'll show you how to do that. So over here, reset word, and if you watch it, the robot will just snap back into place. Okay, let's run it one more time before we get out. So I need to go to my MATLAB environment and then run it again. So you can see it's a circle of radius 2 meters, see? 2 squares. Each square is, it overshoots. You see it overshot a little bit. Yeah. So that's because each time they are adding some random elements in order to make it look like a real world robot. In a real world case, you will not be able to repeat what a car does. For instance, if I asked you to walk 100 steps and we do it 10 times, you'll end up in different spots. So they're trying to, oh, what happened here? Because it finished, I guess. See, that filled out. That was just a glitch. And now it's still a little bit short. Let's run it one more time because it's kind of fun to do. So first I go to the word and reset it. It moves a little bit. And then I come to the MATLAB screen and run it, and this time we'll watch the whole thing on gazebo. So it slightly overshot the 2 meter, and it seems to be overshooting it this time also. So I do know that in the same software associated with other robots, commercial robots, like there's a company called Cleopatra, operating out of Canada. They do add some noise to it because they don't want to have the simulator robot do the same thing over and over again, because that's not how real robots work. There's always will be a slight difference, because maybe your right tire is on a slightly different spot and the friction is different there. So the friction is different there. If it's more slippery, the odometry, right, the wheels are going to rotate momentarily like this, right? And those micro slips are happening all the time. You don't have to be on ice to experience that. Even if you walked on the hallway, there are micro slips happening underneath our feet, particularly when it's polished like this versus rough. Is that okay? Any questions on this? Because anything you build is going to be based on this. So you can take this program home and play with it. You can change the radius. So to change the radius, you can do it one of two ways. Actually, more than one of two ways. So where is my radius? Here. Have I calculated my radius? Here. So you can either change the velocity, keep the rotation rate the same, or change the rotation rate and keep the velocity the same, right? And there are any number of combinations. Now remember, the Turtlebot 3 is a physical robot. It's a physical robot, right? So it has physical limitations. Can you take your own car and run it at 200 miles per hour? No, it's not going to happen. It has some physical limitations. So the Turtlebot 3 manual on the Robotics website tells you that the maximum forward velocity is 0.22 meters per second. I'm actually running it a little bit higher than it's supposed to. But this is a simulated robot, not the real robot, right? So it does appear to be running at that. But I've seen robots from other companies where it won't run beyond a certain value. It'll start to spin and do crazy things. So try to stay, don't go higher than 0.4, and you can look up the rotational rate limitations. So try to stay within the limitations, but you can take the velocity up to 0.4. The reason I say that is the gazebo floor is tiled 1 meter by 1 meter. So this is 1 meter by 1 meter. And so if this robot is only running at 0.2 meters per second, it's going to take 5 seconds to cross this floor. That's why I doubled it. Because we can't wait forever for the simulation to take place. But the real robot is the real robot. You can't run it any faster than it can run, right? Here we can play games a little bit. Okay, so this is done. Any questions on the software setup? So I realized that Wednesday was quick, and it's a good thing we encountered the problems and we are on the way to solving it. Or hopefully we'll solve it. Let me tell you one other thing that may happen. So I need to go back to the way this command is structured. So ROS launch, right, is the launch command. This first argument is the name of the package. So the package has many launch files. So this tells you where the package is, and ROS is set up so that no matter where it is in the directory structure, if you've installed properly, if you've done the source command properly, it will go find it. In fact, this can be tab completed. If you just type TUR and then hit tab, it won't complete it only if there are multiple options beyond that point. But if there's only one option, it will just complete it. Similarly, there are multiple launch files, right? We want the empty world, but there's already a house. Remember that there's a house you can launch, and there's also the Turtlebot. The environment looks like a turtle, so you can launch different things. So in that directory, you find many launch files. You can try launching them. So this launch file may have a problem in your version. It had in my version also, but we figured it out a couple of years ago. I'll show you what that problem is, and here it is. In the team's website, now this is not your website, it's for the other course, but I'll copy these files. They are patch files. So this is the medical robotics course, right? I can copy this into your team's site also. So there are two things here. So some transforms, see when you have a wheel, right? The robot has to know the transformation that applies between the wheel and the robot's axis. Otherwise the wheel spinning, the robot is going to say, I don't know, I don't care, right? Those transforms are not being published in the basic launch file. I don't know why, but we found that out by Googling, and here's what you need to do. So these are the patches. So if you're adventurous and you're familiar with Ubuntu, all you need to do is open up that launch file. You can open it up with gedit, the Ubuntu program, and copy these to the very end, the green. Copy it to the very end. And I told you how to do it. Or, if you don't like that, it's too much for you, you can replace the launch file with the one I placed here. Did you see that? I did put a launch file there. So you got the idea? Either you patch these lines or you take the entire launch file and drop it in there. I'll show you
the launch file also. Right now it's on the other course, but during the lunch break I'll move it to your course also. Now, when you edit system files, it might tell you that you don't have privileges. In Linux, it's a regular feature because they want to protect you from yourself. They know that we do silly things. So those files might be write protected, in which case you have to use the sudo command in front. Sudo gedit, and then you'll be able to edit it. If you want to replace it, means that you'll move a file from, maybe you downloaded it from Teams into your downloads directory, and you want to move it, you'll have to do sudo. Otherwise it will not replace a system file. I suggest replacing it. That's the easiest option instead of opening it up and patching this. But you can see all kinds of publishing is being, the joint state publisher is not even there, and it should be there. Okay, so let me close this. So this is the patch suggestion. This is the full file. Take it and drop it on top of the old one, or delete the old one and move this there. I will have this up during the break. Okay, I think we can shut this down. For now, if necessary, we'll open it again. So you know that Linux has many open processes, and you should shut them down. You shouldn't shut them down in the sense that if you shut it down right at the beginning, gazebo will be gone. Now you're ready to shut it down. It's an eternal process, so you have to hit Control-C. It takes, I don't know why it takes so long. They're doing some cleanup, but I don't know how the cleanup is going to help me because I'm shutting it down anyway, but it does take like 15-20 seconds, and the screen, gazebo screen should vanish, and there it is, it's done. Same thing with Arvis, it needs a Control-C, and Arvis is quicker, then there's nothing there, it's already done. And maybe I'll get out of this. So this Linux computer is very powerful. It's every bit as good as Mac OS or Windows, except that it's open source. And because it's open source, it's free. You can do lots of things. You can set up dual boot on your Windows. It's a little bit harder on Mac, but Windows it's easy to dual boot. You can actually have a separate solid state drive booting up with Linux. Not all Windows, but many Windows machines allow that. And it's a powerful thing on your resume. If you can show a potential employer that you've done these things on your spare time, you've studied ROS and robotics, and maybe you've done a little project. So as I said, you have to become a learner, not just a person who stores information, because the human brain doesn't have capacity for storing much information. All right, so let's move on to the next topic, kinematics and controls. So I did post some files. And the first thing we're going to start with is the introduction to kinematics and dynamics file. I'll show you what that is. Okay. So this is the robot that one of my doctoral students is working with. The one on the top, which is the Pioneer P3DX. It's quite a solid robot. I think it's about 35-40 pounds, so not easy to carry upstairs, The company is now out of business. They don't make this anymore. But before they went out of business, we had advance warning and we bought up 10 of the robots, just in case we needed spare parts for the ones that were working. So it's quite a rugged robot. There are some dynamic effects. You'll get to know what dynamic effects means in the context of a mechanical system shortly. In other words, it doesn't turn instantaneously. Well, nothing turns instantaneously, but some things seemingly turn instantaneously. Others are slower, right? We still have cars that zip in and out. Doesn't mean that they are overcoming dynamics. No, they just better capable of overcoming it, but nobody can overcome dynamics, right? It's a physics principle that is inviolate. It's not possible to overcome it. So the basis of this topic, which is the first thing I do in all the classes, why are you studying this topic? Because then if you can't answer that question, you should not go any further. So different robot architectures, and by the way, here you see a differentially steered architecture. There are two drive wheels, so here you can only see the two drive wheels. They are independently driven. So if the right wheel is driven at the same speed as the left wheel, you'll be going forward, except you won't. In the real world, the two tires don't have the same friction, even if it looks like that, right? If you lay carpet, for instance, you'll find that the carpet is uneven. So even if you drive it at the same speed, it is going to veer left or right depending upon which part of the carpet it's catching, even new carpet. So that's true of floors also, right? All I have to do is pour a little bit of water in front of one of the wheels and it's going to slip more than the other wheel. So it drives straight. Even in the simulator, I told you they are programming it so that it doesn't drive straight. It does veer, and that's good because we don't want something that is artificial. So if you want to turn left, you spin the right wheel faster than the left wheel. And if you want to not spin, turn left. If you want to turn right, then you spin the left wheel faster than the right wheel. And then you can do the same thing with backwards motion also. You can turn them backwards. Now, if you turn the right wheel forward and the left wheel backwards at the same speed, you will spin in place. Is that clear? So, all kinds of sophisticated contours are possible with this robot. Now, in a regular car, if you're driving a car, right, and somebody says, get to this spot, not possible. You have to go and come back, right? If somebody says, get to the next parking spot from here, no, you have to drive over and come back. But this one can. It can turn around in place and actually go there and then straighten itself out. So that is the beauty of a differentially steered vehicle. It is capable of very sophisticated contours, all with that circle concept. You know, the circle, little pieces of circles. A self-driving car can do circles, but it can't get to, you know, a spot immediately next to it. So, the thing that makes it work is, of course, those two wheels plus the caster wheel. So the caster wheel is a passive wheel, and it. Okay, let me see if I can pull up a picture of a caster wheel. We still have that wheelchair or no?
Yeah, we do.
Yeah.
Want to do it? Pull it up now?
Well,
Give me a break.
maybe they can. If you just put it up there so that they all can see it. So that has caster wheels. This is the old wheelchair which they don't make anymore because they've gone to a driven form of the wheelchair. In the sense that now you steer the wheelchair. This one is a differentially steered vehicle, so you need to have a joystick. And if you go like this, you know, you're making the right wheels go faster than the left wheel. If you go like this on the joystick, the other way around. So you steer it using a joystick. Now they have wheelchairs that are steered just like a regular car, you know, the handlebar. Yeah, that's enough. Yeah, thanks. Yeah. So you see there, it has two caster wheels in the front. So you can have one caster wheel, right? But if you have two caster wheels, there's more symmetry and support, right? Because then their weight can be distributed. So that's what it is. It has two nice motors. It doesn't have any controller or anything like that right now. But it can be built up again. So that had a joystick to control it, right? This one is controlled. You can have a joystick to control it too, but it's typically it's meant to be autonomous, and so a computer program gives it the instructions to drive. So the caster wheel just cooperates. Its job is to cooperate with the drive wheels. So this vehicle will roll all the time. It always rolls. There is no skidding. Well, of course, if you give it a kick from the side, it's going to skid. It's actually quite heavy. You might break your leg, so you have to be careful. Maybe with boots on, you can push it sideways when forcing it to skid. It's not meant to skid in normal operation, is what I meant. Any vehicle can be made to skid. Even a regular car, if you push it from the side, you get 4 or 5 guys together. A light car, you can push it and make it skid. So there are skid steer vehicles whose architecture and the way it moves is different from these vehicles. We'll see pictures of those later. But this is a vehicle we like a lot because you'll see from the equations that we're going to derive this morning and later this afternoon that it's a very sophisticated vehicle. Okay, now different robots including cars. So I've given you an example here, a big limousine, maybe we should put it back in projection mode again. Yeah. So a limousine and a Volkswagen Beetle, they don't behave the same. So therefore, in order to establish control, you first have to have a feel for how the robot moves. What are its capabilities in terms of moving? Can it take a short turn, or is it like a limousine? I'm talking about cars. You know that the self-driving car movement is quite big. So they have to figure out what is this vehicle capable of doing in order to establish control. One requires the other. So the Mars rover, you may have seen pictures of the Mars rover. That's a different vehicle from a Volkswagen Beetle. How do they establish a control system for that? They have to know how it moves. And one other point is, you never, these days, maybe they did it in the 50s and 60s, but you never design an engineering system without first going through a simulator. You don't just go and start building, because there'll be so many possibilities that you will not eliminate by going directly to building. You'll waste so much time on building things that ultimately are found to be wanting in some way, that it'll be a lot of waste of money and time. So no engineering product, or very few engineering products, are done without. So imagine a Boeing designing an airliner without ever simulating the individual systems. So you need good models and simulation also. So what is a model? A model is an abstraction of the real vehicle, right? Because in order to design a control system, you don't need all aspects of the real vehicle. I'm making a silly point here, but I think it makes a good point. You don't need to know what color the robot is painted, right? So the model removes all the unnecessary things and only keeps the most essential things there. And you design a controller on that basis, you test it out in a simulator, you save a lot of money, you eliminate choices that won't work, and ultimately maybe you have 2 or 3 choices left and you actually go and build and test them. So that's typically the engineering workflow. You eliminate all the unnecessary effort in the simulator. It's much faster to simulate, right? To take something outside and test it is going to take much longer than, running a simulation of it. Okay. So basically, I've said all this. Maybe I should have flipped the slide forward as I was talking. Model is abstraction of important aspects of actual vehicle. So we need to know that. So in order to know how to control the robot, there are 2 aspects to how it moves. One is kinematic motion and the other is dynamic motion. And it's very important to understand the difference between the 2. Now you'll find many people going with kinematic models and not going to the dynamics model. But maybe I hold that thought, because I first need to explain what is the difference between kinematics and dynamics. So let me just say that dynamics is the more realistic but the more difficult aspect to handle, and many people ignore it, not because it's unimportant. Maybe it is unimportant. If you have a very powerful robot, right, with high torque motors, and the robot happens to be very light, then you can ignore the dynamics aspect. But many people ignore it anyway, whether this particular statement I made is true or not, and they do it out of convenience. Human beings do a lot of things out of convenience, not necessarily out of sense, common sense. We do it out of convenience, and when we do it, what we are saying is, I'll come up with a controller that works with the kinematic model, and then I will let the control loop handle any divergence from the kinematic behavior. So they're basically saying, I'll build the controller this way, but then, maybe it will correct the loop, and it will, right? But the question is, how much of a correction can you afford to have? Why not design a controller with knowledge of the dynamics? That will be a much better controller, right? So they are saying, I'll let the loop handle it, because control loop is basically, if you're not making the path, it's because the dynamics is kicking in. It's too heavy. So they just wait till it corrects itself. So these are the formal definitions from Wikipedia. I'm not a mechanical engineer. There are probably much better definitions in a mechanical engineering textbook. So kinematics is a branch of classical mechanics that describes the motion of points, bodies, systems of bodies, without considering, forget all that stuff here. This is the most important. Without considering the forces that cause the motion. So you go from the motion itself, but remember, force is upstream. How did you get motion in the first place? Suppose the thing is stationary, how is it going to move? You're going to apply a force to it, right? And you know Newton's law, F is equal to ma. So force causes acceleration, and acceleration causes the velocity to change. You forget all that. In the kinematics model, you say, I'm going to act as if the velocity is available right away, and it's going to change right away. Big assumption, right? But if your robot is light, and or the motors are very strong, then maybe you don't need to consider dynamics, because the velocity will be changing fairly quickly, not instantaneously. It's not possible for velocity to change instantaneously, ever. But maybe it's fast enough that you don't care.
So, forces are not considered here. Dynamics is a branch of physics concerned with the study of forces and torques and their effect on motion, as opposed to kinematics, which studies the motion of objects without reference to its causes. So, rather than read those bullets, I believe I still have an earlier document that I can use, but maybe not. Let's see. Oh, I'll tell you what, I'll do it again. So I'm going to open a blank sheet here, because I don't want to roll the screen down. So everybody remembers this equation, right? Ignore the capitals and all that. Microsoft Word is doing that. So this should be a lowercase. This might remind you of your physics days. Here was V is equal to U plus AT. Remember this from physics? What they never told you, and my physics professors in IIT and earlier in high school never told me this. This is a model. This is not the real world. So I always believed that the real world subscribed to this, right? Now, the real world would subscribe to this if the acceleration were to be a constant. Who can hold the acceleration constant in the real world? It's not possible. No physical engineering system, right, can maintain a constant acceleration. It will change. Look at the cruise control of your car. When you reach, if the road is like this, it's going to slow down a bit, right? But when you're a child, a kid, you tend to believe that these are all reality. They're actually models of the world, right? Of course, in those days you could not ask these questions because they would show you the door. Is that true even nowadays?
Some classes here.
Yeah, so you could not ask this question. This is a mathematical model. That's all it is. Now, how can I change U to V? Why would I want to do that? Remember the circle? R is equal to V by omega. If I wanted to change R immediately, right, I would need to change, let's just take V immediately, right? How is V going to change from an initial value of U to V? Only if you have an infinite acceleration, isn't it? Now what does that mean? F is equal to ma. So to have infinite acceleration, either the mass has to be zero, or the force has to be infinity, or maybe both. Never going to happen. So there's always going to be a delay when you change velocities. That's something that you cannot eliminate. No matter all this talk about going to Mars and so on, there's no way of on Star Trek, if you watch these sci-fi shows, they show the spaceship suddenly accelerating to infinite speeds. It's not possible because physics basically places a restriction on that. So it's always going to take time to go from Earth to Mars. I don't see how they can get around that. So that's the problem. That's the difference. In dynamics, you start from here. In kinematics, you start from there. Just from V. You assume the V is available to you. Don't worry about the upstream. Upstream, you know what upstream is? That means when a river is flowing, right? Force is upstream. Then you go through F is equal to ma, and then you go through this equation, and then you get to change the velocity. We just jump on the change in velocity and say, okay, it's happened instantaneously. So that's the difference. So basically, this is saying that same thing. So at least you need to know the kinematic capabilities. You can't ignore that also, right? Because then you will not realize that a regular car cannot move here from its current position, and then you'll be kicked out of the company you're working for. So at least the kinematic model is needed. So kinematic, you can visualize kinematic as if you move the car very slowly, what are its abilities to curve? So imagine your car is broken down, your friends are pushing it, right? And you want to turn into your driveway. Now you want to slow down basically because you might not make it because you don't have power. So you know how the wheel doesn't turn easily when the vehicle is stopped, but at the same time you don't want to go too fast because you might miss this. So imagine your friends pushing it very slowly and then you're turning it. That's basically kinematic motion. What are the kinematic capabilities? That's what it is. And by the way, both kinematic and dynamic, when you buy a new car, you go for a test drive, right? You are trying to gauge both the kinematic and dynamic capabilities. Because when you're driving around, right, don't you turn into a driveway and then you see how it moves from lane to lane. You're trying to get your brain and body to understand, do I like the kinematics and dynamics of this vehicle? Now you don't need modeling to do that because the human brain has this ability to pick up what this car is doing. Some are better than others, right? You drive it around for 10 minutes. I don't know what the practice is here, but in the US they let you drive it. If you don't show up after 2 hours, of course you're going to call the police. But they used to sit next to you in the old days. Now they don't even do that because I believe they may have GPS on it, so they know where you are. But of course, if you take off to Chicago, then they're going to call the police. But basically, 10 minutes of driving, you get a feel for it. You take it on the highways, you go fast, stop, they brake hard, take a ramp, you do all kinds of things to figure out how the car behaves. So that you're really trying to model it in your head. So once you know how it moves, then only you worry about the control for it. Okay. Oh, do we need to increase the resolution for this? So this is something my my student found out just recently. He's working in the area of designing robot parts. In other words, coming up with a model for the robot. Now, human beings don't need a model, right? When you're trying to buy a new car, but a computer does. So he's trying to come up with a method for modeling any robot, no matter how you have distributed the weight, how many wheels. He has an experimental, he's trying to develop an experimental method. He's almost like 75% done with his thesis. How to come up with a model that then can be used to design. So once you have a model, you can use a simulator and computer software to devise a navigation strategy for it. That's what he's doing. Because when they build robots rather, it doesn't come with a model. They don't have a tiny USB drive saying here's the model. You're pretty much on your own in figuring out how it moves. So that's what he's doing. Basically, he'll be able to design or extract a model for any robot. So what you see here is a figure of 8. The Pioneer is doing 2 figures of 8. The Pioneer, remember that vehicle I showed you in the first slide? It's doing 2 figures of 8. And it's actually starting right here. So this is the robot, that's the front of the robot, right? The 2 drive wheels are here. It's starting here. And then it's going around the figure of 8 once and then twice. So the first time it takes this part, 1 and 2, it doesn't stop here. It goes right through to 3 and then to 4 and then to 5 and then to 6 and then to 7 and then to 8 and it's brought to a stop. Now notice when it's initially stopped here, V and omega are 0. So if you want it to be on this circle, then you have to tell it V and omega, right? But it's at 0, 0. So 0, 0 is not going to immediately become V and omega. There's going to be the acceleration phase. So on 1, which wheel has to eventually reach a higher velocity? Left wheel or right wheel? Right. The right wheel, right? But they both started at 0, 0. And I'm assuming that they have the same motor. Why would somebody use one brand of motor here and another brand of motor here, right? So I'm assuming they have the same brand of motor. So isn't it true that the right wheel is going to take longer? Like, first of all, they're going to go exactly next to each other, right? Till they reach the lower of the 2 velocities. Doesn't that make sense? So what does it mean? These 2 are going at the same speed till the lower of the 2 velocities. It's going to go initially straight. So even though you expect it to be on a circle, it won't get to that circle. And in fact, if you blow this part up here, you will see that it's actually going straight till the lower of the two velocities is reached. Then the right wheel keeps on going, the left wheel has reached its target velocity. And then it starts to get on the circle. After that, robot never stops, right? Except, what's going on here? Over here, how do you make it go? So here it's going counterclockwise around the circle. Here it's going clockwise around the circle, right? You know how you do that? You make omega negative. So you see that when we get into the equations. When you make omega negative, it starts going counterclockwise around the circle. So basically, you're exchanging speeds. Do you realize we're exchanging speeds now? Now the left wheel has to go faster than the right wheel. Does that make sense? Because over here, the right wheel was going faster than the left. Here, the left wheel has to go faster. So left wheel was going slower. Now it has to go faster, so they have to cross over. So again, you're forced to go through the acceleration phase. And so over here, you will see that it's not quite on the circle for a while. Till they reach the target velocities, you're going through Newton's law. There's a delay. So you will not really be on this final circle for a while. And that's the very same reason why the next go around doesn't look like this. So 3, 4, 5, 6, 7, and 8. So this is a good indication of dynamics, a simple experiment to show that, So why would you care? It's because when you're telling it V omega, right, and you think this should go through that gap, realize the delay, because you have to compensate for the delay, You can't just say, I have a circle here, that circle geometrically penetrates the gap, so I'm okay. Because there is a delay. You don't get the circle immediately. And therefore, your navigation strategy should know the dynamic capabilities of the vehicle. That's the same thing we do when you buy a car and we've driven it for a couple of days, we figure it out. How do you get the computer to realize what the robot is capable of? You need models, We don't need models. Some of us are better, right? Some people crash the car within 2 days because they haven't really understood the car. And others, are better at figuring out, what the car is capable of. So we're really trying to model it in our heads, but in the case of the computer, it needs a mathematical model. So a quick word, on the difference between manipulators. So manipulators have been around for decades. I would guess, but you have to Google it, probably the 50s, or 60s. That is the previous century, 70 years ago. So then, because I think Henry Ford, he was the first one who came up with this assembly line concept of a car, and they must have had these robots to do welding and so on, but we'll have to look it up. So essentially that branch of robotics has been around for decades, right? Mobile robots are more recent, self-driving cars and all that are, very, very recent, last 20 years. So what is the difference between the two? So that branch, I call it manipulators, maybe there are other names for it, it's like welding, the car goes by, you weld, another car comes, you weld, so that is a separate course. So in our university we have it as, back to back. The fall I teach the robotics course, meaning the mobile robotics course, and then in January, it's going on right now, a person from mechanical engineering teaches the manipulators course. So, for instance, maybe you're sorting parts in a bin. You pick up a part, put it here. You pick up a part, put it here, right? So the difference is the base is anchored. So because the base is anchored, it makes certain tasks very easy. And the biggest task is localization. Because the base is anchored, and all these joints, you know the lengths and how much each joint is rotated, then pretty much most of the time it's possible to figure out, we call this the end effector, because ultimately the robot is doing something like welding or picking up something, so you pretty much know where the tips of the robot, if the robot has fingers, typically they don't, we are welding, fingers won't do you much good, you're welding. So pretty much you know where the end effector is. And you know, the problem has been solved for decades now, because remember, you don't want the welding to be done on a random basis, because who will buy that car, right, if the weld is all over? So there is a certain precision involved, but localization is easy, because the base is not moving. On the other hand, for a mobile robot, you're moving all the time. So localization is very important. Now, one of the mistakes we make is we view localization through the eyes of a human being. So when we walk down the hall, we don't need to precisely localize. You know, it doesn't matter that we hit the same tile every single time when we are leaving class, because we have other things going on in our head that helps us to overcome that. But imagine a robot that is going through a minefield. Localization means something different for a robot going through a minefield than you and I walking to a restaurant to have food. Because I can afford to be in error, right, by a certain amount, but a robot going through a minefield has to be quite precise, knowing that it can't be 100% precise. Remember, nothing can be 100% precise. So, but it's still a very tight precision for a robot going through a minefield. Surgery, you got to be very precise, right? You can't be operating on the wrong part of the knee. So it depends on the application, is my point. And mobile robots have always had this problem that localization is not easy because the base is not fixed.
In the manipulator on the manipulator front, we are answering questions like, is it capable of reaching a certain point?
Right? Can I go underneath this table and pick something up? Now, of course, in an industrial environment, you clear the space. See, that's the other thing. For manipulators, you can clear the space and ask humans to stay out and all that. For a self-driving car, you have to operate amongst the general population. So it's a much more difficult problem.
So, for instance, the mobile robot, can it operate in an extremely cluttered environment to reach its destination?
So imagine if you have an earthquake and robots, so this is increasingly happening, by the way, search and rescue, because we are increasingly having, you know, much more violent storms, flooding and so on in the US. So they're trying to come up with robots that will avoid risk to human life, you know. Basically, we call them first responders, police and fire people, send robots in first. But when you go into an earthquake area, then you have to ask yourself, you know, is it capable of operating in that area? How will it localize itself, etc. Maybe the whole infrastructure is gone down, right? So those are the questions that need to be answered for a mobile robot. Can it squeeze through, you know, small gaps? So if they have snake robots, by the way. So when you have seen all these videos from the earthquake areas, where they ask everybody to be quiet and they listen for sound, you know, to see whether a baby is crying or, you know. So they now have snake robots with, you know, microphones, water and everything that they send into the cracks of an earthquake disaster area. Because the human being obviously, you know, cannot go through those cracks. So these snake robots, you know, they go through, they have infrared seekers, so they can find out whether anybody's breathing and still alive.
So this is a robot that we have. This is a fixed robot from this company called ROS, and this is our Pioneer. So I just wanted to put it there for comparison. So manipulator environment might be easier to constrain. You can, as I said, you can clear out all the furniture. They call it furniture, and make it antiseptic. So it's just the robot and whatever it's doing, right? But you can't do that for a mobile robot. But on the other hand, many more degrees of freedom are involved. So our right arm has something like 23 degrees of freedom. Did you know that? Just the right arm. Because each joint, right? Wrist, elbow, and count, it's 23 degrees of freedom. Now, most of these manipulators don't need that many degrees of freedom. Because too complex is not a good idea unless it helps the task. If you just make it too complex for fun, then you will not be able to sell the product, right? Now, of course, if somebody says, give me 5 of your degrees of freedom, I'm going to chop off these 2 fingers, you're not going to allow that. So a human being is more sophisticated than needs to be, right? But a robot doesn't have to be that sophisticated. You don't need 23 degrees of freedom in one arm. You need many fewer, but it's still a lot more than mobile robots. How many degrees of freedom did our robot that we ran in a circle have? 3. X, Y, theta.
just 3. And in 3 dimensions, 6. So a drone will have X, Y, Z, and it will have 3 angles. That's quite complicated by itself. But those manipulators, they easily exceed that number because of all the joints. So, here's the difference in where they operate. Typically, they operate in structured environments. That means man-built factories, right? So you can control the environment. Mobile robots are anywhere in the world. So you really don't, they're unstructured environments. They can also be indoors, but most of the time, they can also, they're outdoors. Okay, we don't need to go through this again because, we've already seen. Well, so maybe we do. Sorry, this is for robot manipulators. Let's go through it. Forward kinematics is the process of calculating the position in space of the end of a link structure given the angles of all the joints. It is relatively easy and there's only one solution. So there's only, if I tell you this shoulder joint is at this angle, and this angle, anybody can figure out. There's only one solution, right, of where the tip of my middle finger is. So that's called forward kinematics. But if I ask you a different problem, I want you to pick up this cup which is sitting under the table, right? So maybe you can go like this, or like this, or you won't do this, but maybe you want to do this. So do you realize there are many solutions, and there is an optimal solution there? Because if you're on a shop floor, you don't want to be doing this just because it's fun. You want to take it to the shortest path without hitting an obstacle, right? Because maybe you're just packing, so you want to move a lot of parts so that you make money. So in these ports of ours now, well, ports in the Western countries, but now in our ports also, you unload these containers, and the quicker you unload them, the less the ship has to pay, because while it's being unloaded, the charges are based on hour. So you have to do it fast, So that is like an actuator in a sense, because you pick it up and you take it, you can't just throw it, right? You have to properly organize it, and then you go get another one, and the faster you unload, the less money that the owner of the ship has to pay. So there is a certain optimality involved. So most of life involves optimality. We want to do things in the best possible way. So this is for mobile robots. So that definition was for manipulators. This is for mobile robots, the same thing. Did we go through the opposite? No, we did not. So inverse kinematics does the reverse. Given the endpoint of the structure, what angles do the joints need to be to achieve that endpoint? You can add in an optimal manner. So there are many possibilities, right? So what are the angles in time? In time, because only then I'm going there, right? All these angles have to be allocated versus time, because if I don't do it, I might hit this. So maybe I have to do this and then go forward. You see what I mean? It can't be any angle any time. So there is a sequence involved. So that's what you're doing when you're doing reverse kinematics. You're trying to figure out, okay, if I need to get there, what should I do with the angles in time? The same problem is there for mobile robots also. Estimating a mobile robot's motion and or pose. You know what pose is? Pose is a short form for x, y, theta. So it's not just position, it's position and theta. So it's a short form in robotics. So estimating a mobile robot's motion, the motion is, I've got there, right? But how did I get there, Like where was the robot? Here, here, here. So imagine plotting x, y, theta along the way. So if somebody tells you V omega is a function of time t, there's only one answer. Everybody should be able to figure out that one answer, because it's those little tiny circles, right? So if I give V omega versus t and I give you 10 pieces of data, everybody can get to the same answer. There's only one answer. Now I reverse the problem. I need the robot to go from here to here. What are the commands needed to go there? That has many solutions. I can go like this, I can go like this, right? So there are many solutions, you agree? And that requires optimization. You can't make money on forward kinematics because the computer will do it much faster than you can do it. Do you all agree? There are programs that do forward kinematics for both areas, manipulators and mobile robots. Nobody's going to make, this AI is already scary because computers are doing more and more what we thought only we could do. So where is the need for human beings to be there on the job? So they're actually stealing even those jobs which required mental power. So it's going to be a challenge for everybody here. You are at the beginning of your careers, and so you're going to have to worry about, where can I add value and show brain power that the computer is not capable of showing. So that is the key to having lifetime employment. You have to do something that the computer can't. So all computers can do forward kinematics in both areas, manipulators and mobile robots. But only some human beings can do the reverse problem. But if we take our knowledge and put it into a computer, that's it. We're not needed anymore. Because then the computer can also do, reverse kinematics. So okay, so that's the end of this set. So this is a big deal in Western countries. There's a book by Sequard, one of the prominent books on robotics. And you'll find many of these PowerPoint presentations use these figures. And if you don't acknowledge them or get permission from them, it is considered plagiarism in the West. Some people don't, because how many people are they going to prosecute? But you'll find these figures in many presentations. So it says figures courtesy of Sequard and Ulbach. I try to do that as whenever I'm conscious about it. Sometimes I miss one or two. The reason I'm cycling through, because we did say we're going to start from 21, is to show you some other interesting pictures here. So, see all kinds of motion that they're trying to model. Snakes. So snake has a particular motion, it's side to side, it goes like this, and by doing this it goes forward, So they try to model it only because they're trying to build a robot that will do the same thing. Animals can teach us a lot because they function in their own environment and they are best in that environment. If you put a snake, on a road, it's not going to be very good, right? So they are designed by nature, God, in order to work well in that particular environment. So the idea is that humans can learn a lot. It's called biomimicry. So the area is known as biomimicry. It's a big part of robotics where they're trying to imitate things found naturally in the world. Yeah, so here is a snake robot. It's not a video, otherwise I would play it. So this is not an actual snake. It's a robotic snake. You will find videos of it moving on YouTube. And these are drones. Here is a model of a human walking. So again, the idea is that, of course all humans don't need a model to walk. We learn it when we are very young. But if you're trying to maybe design a false leg for somebody who's had his leg amputated, then a model might help as to exactly how you will build that leg, right? This is from a research study. You'll find the reference in Sequard's book. That's a real robot actually. It's used to cut trees in the forest, and it looks quite scary. If you can pull it up on YouTube. It may be owned by John Deere, which is a very big tractor company. It has multiple degrees of freedom, because here wheels won't help. You need something beyond wheels, and so that's what it is. It's probably quite expensive to run, but in this terrain, even an SUV is not going to work very well. A sports utility vehicle. Okay, that's the cost of wheel here. So you see this wheel here? It's called a Swedish wheel. Swedish wheel 45, Swedish wheel 90. So you know what it is? Let's go with the Swedish wheel 90. So if you have a robot with 4 of these wheels, it is capable of going sideways. Now, these sideways rollers, so by the way, this can roll in this direction, as well as the whole wheel can roll sideways. So it has 2 degrees of freedom, right? No, it can also spin like this. right? So what's the purpose of this? Imagine, one of the most difficult tasks for all of us, parallel parking, right? Is quite difficult for most of us. Some are better than others. You use, again, this is the era of social media. You find people posting videos on how they parallel park at high speeds. I don't know whether it's fake or not. He'll be coming in at a rapid pace and he'll manage to squeeze it into a small gap and stop without hitting the other two vehicles. But it's a skill. You can practice it. Most of us are occupied with other things. But these guys, obviously, this is their employment. So you can see them parallel park at high speeds. Well, if you have a vehicle with these kind of wheels, then parallel parking is easy because you can slide sideways. Now nobody will watch that video on YouTube because it's not that exciting, right? Just coming here and then going sideways. But also note the additional degrees of additional degrees of freedom incorporated makes it a problem for normal driving. It is not easy for a human being if the sideways degree of freedom is opened up in regular driving. You will crash. If the vehicle could go sideways, and you have all kinds of people on the road with that kind of vehicle, you're going to have massive crashes. So it's better sometimes not to have too many degrees of freedom. It makes the job of controlling it easier, but it also prevents accidents. So yeah, here it is. See, this is an actual picture with the Swedish 45. Okay, let's go to the target, which is right here. See, slide 21. So we're going to learn a little bit about frames here. There's a separate topic about coordinate transformation, frame transformation. We'll probably get to that, I'm thinking tomorrow. But this is just basic understanding of frames, without which you can't do robotics. I already turned on the frames in ROS, right? You saw all the frames for just the robot. But if you imagine multiple robots, there's so many different frames. Now, why do you need this? That's what I'm getting at here. Why do you need transformations? And also in the process, we're going to derive the equation that led to R equals V by omega. How do we get that? So we're going to derive that for the differentially steered robot. So we have global coordinate frames, and then we have local coordinate frames. So local is from your perspective, right? Obviously, it's convenient for you to use your local coordinate frame. But there are some global coordinate frames because other robots can't use your local coordinate frame. They are using their own. So in order to share information, we have to work through a global coordinates frame, right? We have to take our information and put it on the global coordinate frame, and then the global coordinate frame to the other robot. So that is really what is happening. You can think of the global frame as a control tower, central control tower, and everybody is passing their information. In other words, the information is changing perspective. Because the local coordinate frame perspective is your perspective. If you describe to your friend, okay, I'm saying this in front of me, he'll want to know where you are and which direction you're facing. So that's what is happening in these frame transformations. So global coordinate frames and local coordinate frames and the transformations required to pass information between them. That's what these three items are. And then we're going to obtain the equations for a differentially steered robot in the kinematic mode. We're not doing dynamics anymore because it's beyond the scope of this class. I told you there's a PhD student of mine working on that separately, trying to model a robot's dynamics. So whenever we want to control the robot, right, we need to define what are the variables we're interested in controlling. So for instance, it could be x, y, theta. So then we create a state vector with those three stacked in there. Now, many times when they use an example in robotics, they'll say, let's assume you're only controlling x. And that's because if I jump directly into controlling three variables, then I have to bring matrix terminology into the picture. And then all of a sudden we're stuck in the mathematics. We are not understanding the concepts because the mathematics has bogged us down. So therefore, when we actually do an example, we'll just work with one variable at a time. That's how we learn, by the way. We learn from the simple to the complex, not the other way around. So the point is that if you want to control a whole bunch of variables, then you put it in a state vector. Okay? Don't put things there that are meaningless. The color of the robot, there's nothing to do with the motion of the robot. So there's no point in putting it there, right? The condition of the battery, yeah, that's of interest, but that's a separate control, right? Now, x, y, theta may not be the only three quantities you're interested in controlling. You may also want to control the speed of the robot. So V and omega can be put in there. But remember, I told you V and omega are brought out for your convenience. They relate to the actual motors through the equations we're going to derive for a differentially steered robot. So maybe you want to put the speed of the motors there, because that's really what you can control. V and omega are downstream variables. So then you create a longer state vector, as long as you want it, whatever it is you're interested in. So typically, you have to resort to physics, because differential equations describe how the robot state changes due to the inputs. You have to start from there as you build your model. And then once you have the so-called kinematic, so the differential equations are used to generate kinematic equations. And then once you have the kinematic equations, then you can start designing a controller for it. So the kinematic equations are understanding the motion in the form of a math model. Not just looking at it and saying, oh yeah, I understand that. No, you want a math model for it. Then you can design a control law. So, we have to have a coordinate system. So a global frame is fixed. It is not movable. You can't dig it out and put it somewhere else during the experiment on the robot. So the global frame is also called the global inertial world frame. All these are equivalent names. The global frame is fixed, but you can have other fixed frames. But there's only one global frame, right? I told you this earlier. You can have many fixed frames, right? But there is only one world frame. There's only one. Then you have local frame. And then that could be the robot A. Remember, there could be many robots. So robot A is local frame. So that is the point of view of the robot. Or it could be, it has a camera, 2 cameras, 5 cameras, right? So each one of them has its own local frame. And the problem becomes much more difficult if the cameras are pivoting. No, the frames don't change, but the frame is pivoting. That's what I'm saying. The camera frame is pivoting now, right? So there is no constant relationship between the camera frame and the robot frame because the camera is pivoting. So we have to transform all the time. Just think of a simple task. The robot is in a hurry. They mounted 4 cameras on it to build a map of the environment. So it's looking every which way and it's driving around, right? Otherwise, how do you figure out the map? You have to drive to all the corners. Do you realize that you can't just join all these maps together because they are different points of view? So somehow they have to have the same alignment. And for that, right, not only do you have to first put them on the robot frame, but that's not enough either because the robot was pointing at different parts of the environment. So you have to take it and put it on the world frame because the world frame is never moving. So you want to build the frame on the world, you want to build a map on the world frame. That's how complicated it is. No human being could sit and do all the calculations, that's why computers are there to do it, but we have to understand how it's done. So there may be many local frames. There is only one world frame, but there can be many local frames. So this one, it's a live PowerPoint. It's a PDF version of that, so it will pop up now. Yeah, there it is. So this is the robot. They don't show the differential, the caster beam. Remember the caster beam? That one? They don't show it here. It's there, somewhere underneath. These are the 2 drive wheels, the most important wheels. And as I said, this is the definition of heading in the robotics literature. I found that heading is defined in different ways on the general literature, in the general literature. Maybe with ships is different or something. But in robotics, heading is always the angle made with respect to the world. See, xi, inertial is another name for world. So theta is with reference to this, not with any other axis. It's with respect to the world's x-axis. So that's assumed, that's a convention. Not with respect to the y-axis, with respect to the x-axis. So, give me a good guess for this angle. The number doesn't matter. Let's say plus 45, right? Degrees. Now, degrees is a convenience for us. Human beings like degrees. We don't like radians so much. But anytime you get into the internals of robot software, it has to be in radians. So when you have a bug in the program, it could be because you forgot to convert from degrees to radians. So what will happen if I turn this robot so that it's doing, like it's facing in a mirror image way. So it's maybe it's looking this way. This line is now aligned this way. What do you think the angle will be? So sign conventions are very important, right? So it's minus 45. So if that line dips below the xi axis, it's minus. This way positive, this way negative. Okay, how about if I rotate the robot so that line is pointing here? So maybe 135? How about if it's pointing here? You say 225, right? But that is technically correct, but it violates the conventions of robots. Robotic angles only go from 180 to minus 180. No angle above 180 is allowed. So there is something called unwrapping the angle. So this angle, 225, is really minus 135. Minus 135. Got it? Angles only go from minus 180 to plus 180. Not from 0 to 360. MATLAB has tangent functions which give you the result from 0 to 360. They also have a ATAN 2D, which is meant for robotics, that goes from minus 180 to plus 180. I forget. You can't include 180 and minus 180. You know why? Because you'll be double counting. So either the negative 180 is included or the positive 180 is included. I'll look it up. I forget. I never remember those things. So only one of them is included because you can't have the point in two ranges, right? So this is the robot state. So it's pronounced psi. It's a Greek letter. It's psi. That's why I put this down here. Psi. It's xy theta in the inertial frame. That's what it means. See, psi I is xy theta in the inertial frame. And this is a transpose notation. Now typically state vectors are vertical, right? But in books, if you keep on writing vertical vectors, you'll use up a lot of space. So for that reason, they write it horizontally, but they say they put the transpose in there because it's really meant to be a column vector, not a row vector. So here's the x, here's the y, here's theta. Now first let's define the robot axis. So the robot's axis, remember we are only dealing with a robot on a plane. So z is not relevant, it's going up. You know why it's not going down? Why is z not down and up? Because we have a right-handed coordinate system. This is the convention in robotics. When you turn x into y, if you have a right-handed screwdriver, let's say screwdriver, when you turn it this way, the screwdriver comes out, right? So that's the right-handed system. So z has to be in the direction you turn a screw. Some people use this rule. See, turn x into y, and where is your thumb pointing? Out of the way. So if you're a roboticist working with right-handed convention and somebody else is working with the left-handed convention, there's going to be disaster. Do you know that European rocket about 10 years ago crashed because the Americans were working in the stupid feet, inches, yards, and the Europeans are working in meters. So the Americans, I don't know why they can't give up the yard. Even Canada has given it up. Mexico has given it up. So it's like an island. They still use yards, inches, and feet. So because of the conversion, something went wrong. Luckily, there was no human beings on board. So here's the robot state. x, y, theta, r. See, r. Otherwise, you'd be writing x, r, y, r, theta, r. Not necessary. It's simpler to say x, y, theta, r. And that's psi r. Now, it's 0, 0, 0, right? Will it ever change? The robot is carrying its axis, right? So how can the coordinates of the robot change in its own axis? It's never going to change. I'm saying, okay, what's the point then? Well, you see the point. Not for this, because obviously that's understood. It's for seeing other objects which are not on the robot. So here's an object, and the way you and I see things is exactly this way, through a range and bearing. It's known as polar coordinates. We don't see things on XY grid. I say, I saw my friend, he was about 50 meters away in this direction, right? So this direction means with reference to this axis. We don't see things in X and Y. We don't give XY coordinates of our friends, and say, oh, I saw the person at 50, 30. I saw him off to this side, right? He was talking to somebody about 100 meters away. So range and bearing is a natural way to see something from your perspective. Except that if you want to put it on the global frame, you have to first convert it to X and Y on your robot axis. We'll see how to do that. So range and bearing. So this is the range. Range cannot be negative. It's always a positive number. But bearing can be negative and positive. So the way this object is positioned, right now, alpha object, which is the bearing, is negative. Clockwise is negative. Remember the same convention we saw earlier? Clockwise is negative, counterclockwise is positive. So if this object were to be here, then the bearing would be positive. Again, robot angles, even the bearing angle only goes from 0 to 180 and 0 to minus 180. So once you cross this line, then you have to unwrap the angle. Is that clear? No angles above 180 or below minus 180 are allowed. It's not a 0 to 360 system, 360 degree system. So the measurement is taken relative to the robot's local coordinate frame. That's the only natural way to do it. And then, you understand this, right? Trigonometry. How do I project this to the axis? Rho object times, what is the heading angle? You remember the heading angle? It is the angle made of the nose of the robot with respect to x side, right? But we're not concerned about that right now. We're just projecting it onto XR, YR. So how do I get the coordinates on XR, YR? So rho object times cosine alpha object will be this projection, correct? And rho object times sine of alpha will be this projection, right? You know that from trigonometry. And there it is. That's called the polar to rectangular conversion. Is everybody okay with that? Don't mess with the signs, because the signs will automatically be correct. So in this picture, alpha is negative. Don't make it positive and say, I will figure out the sign. Because if alpha is negative, it will be correct. Alpha object R, right? It's a negative Y result and a positive XR result, correct? And this automatically gives you that. So don't try to change the angle, because the computer can handle it. Now, that was the state of the robot, right? State of an object with respect to the robot. But what about the velocity of the robot? So, d by dt of the position state of the robot. Now you're saying d by dt of that? But that should be 0. Not really. When you say d by dt, even though you're at 0 all the time, right? You're really trying to figure out the rate of change with respect to the ground. So even though it's 0, 0, 0 all the time, it doesn't mean it's not moving with respect to the ground, right? So there is a d by dt with respect to the ground. And sure enough, you get x dot, y dot and theta dot with respect to the robot axis. Is that clear? So this has to be interpreted as velocities in robot axis directions with respect to the ground. You can't say I differentiate 0, I get 0. This is with respect to the ground. So in the direction of the nose of the robot, the velocity is x dot. In the direction this way, because remember, the green axis is this way, not this way. Red axis, green axis, blue axis, right? So y dot in this direction, it could be negative. Theta dot, positive in this direction. Counterclockwise, negative in this direction. So for the differentially steered robot, this x dot is what we called v earlier. Y dot has to be 0, right? Now that does not mean y dot has to be always 0. If I come and hit the robot from the side, of course you're going to give it a y dot, right? Under normal operation, it's not going to move sideways, right? That's what they're saying. It doesn't mean that you can't force it to move in that direction. And then do you realize that theta dot is omega? So for the differentially steered robot, x dot, y dot, theta dot is equal to v, 0 and omega. Only for a differentially steered robot. Okay, now, remember these are from the robot's local perspective. But if I'm so you're driving from Chennai to Vellore, right? And you give me your local v and omega, how do I know where you are on a map? So I have to use the word frame. That's the only way I can plot it, right? So the first step is I have to take your local reporting of velocities and convert it to the global frame. So in order to do that, right, here it is. So this is going one way. I'm taking velocities on the robot axis and converting it to the global frame. This is going the other way. I'm taking velocities on the global axis and converting it to the robot frame. One of these matrices is going to be the inverse of the other. Now, why do they call this r theta and this r inverse theta? Why not the other way around? Because some roboticists choose that. And since he was the first, everybody else has to follow him. This r theta is assigned to converting from the world frame to the robot frame. And r inverse in the opposite direction. So, do you agree with this? xi dot, see? This is where the heading comes in. You take the robot's forward velocity and project it this way, and you project it that way. So xi dot is xr dot cosine theta. And yi dot is xr dot sine theta. But still, how do I monitor your progress from Chennai to Vellore? Let's see. Do you agree with this? Rotation is rotation. It doesn't matter whether it's with respect to your local axis or the world axis. So theta I dot is the same as theta r dot. Now let's get back to the question. How do I monitor your velocity? I'm sorry, your progress, your path, your location at any given time. First you put the equations in matrix form. So those three equations that you saw, for instance, theta I dot is equal to 0 times this, 0 times this, 1 times this, right? xi dot is cosine theta times xr dot, and xr dot and 0, 0 multiply these two. So those equations, because whenever we have more than one equation, it's better to put it in matrix form. See, matrices initially are just a way of organizing data. Of course, after that you can do a lot of math with them, but they help you organize equations, multiple systems of equations. So, the only difference is that is put this label here. This is your psi r dot, psi I dot, and psi r inverse. Now, how am I going to get position? Because what happens when I integrate xi dot? Don't I get xi as a function of time t? No? If I have an equation for dxi by dt, and it is an equation, right? It looks scary because it's a matrix form. It's an equation. Similarly, I have an equation for yi dot, right? I have an equation for theta I dot. What happens when I integrate it? I will get these quantities as a function of time t. Isn't that monitoring your progress? Now, the one qualification is that in most cases, you will not be able to integrate these, because you know that you can always differentiate a function, but you cannot integrate every function, right? You know that it's a fact of calculus. that you can't integrate any function you want. You can differentiate it. But computers can numerically integrate any function. Sometimes they choose to numerically integrate functions for which integrals exist, because computers love to numerically integrate. So you use that integration, numerical integration, as a way of getting the result. And computers do it very accurately. So even if you can't integrate it, it will be able to integrate it as accurately as you want. We used to do numerical integration back in my college days. It was very painful, by the way. Yeah, extremely. You still do it now?
No.
Yeah, sit down at the calculator and do one step at a time, It'll take you hours. I don't know why they made us do all that, but education was different. So what happened here? So what happened here is, notice that YR dot is 0, right? For a differentially steered vehicle. So what's the point of including an equation which is going to give you a 0 result, right? In other words, if I get rid of this, right, what should I get rid of here? See, these numbers are all multiplying YR dot. So why not get rid of that? That's it. Because for a differentially steered vehicle, YR dot is 0, so it's not conveying anything. So 0 times 0, 0 times 0, it takes that part out. The left just doesn't change, it's still a 3 by 1. And now, instead of carrying those other symbols, I use the commonly known symbols, V and omega. So this is the equation that the gazebo simulator is integrating to tell you where the robot is. So if I give V and omega at different points of time, the gazebo simulator is able to pick up those changes and change the integration, and it keeps putting those circles together. Is that clear? That's how model state figures out where the robot is, it integrates it. So forward kinematics. So now with those equations in place, we can define the forward kinematics of a differentially steered vehicle.